Hello guys, this is Shirup Dotto from Expert Mathematica. Today I'll be discussing a question from linear algebra. For this question comes in CSIR NET December 2023, question number 11 and question ID 704075. And this question is from part C. So it has 4.75 marks and we have to check each and every option. Given that A is an n cross n real symmetric matrix, then which of the following statements are true? So we know that a real symmetric matrix is orthogonally diagonalizable. So if A is an n cross n real symmetric matrix, so A can be written as P inverse dP, where P is an orthogonal matrix. So orthogonal matrix means the suppose P is n cross n matrix, the columns of P will form, whatever column we have will form an orthogonal set with respect to each another. So since A is an real symmetric matrix, so a real symmetric matrix is orthogonally diagonalizable, so A is diagonalizable. So A is similar to a diagonal matrix D, where D is the where diagonal entries are the eigenvalues of A, so A is diagonalizable. Now given second option is A to the power k is identity for some positive integer k, then A square is identity. So what we have, so A is P inverse dP. So if we take A to the power k, so if we multiply P inverse dP k times, we will get P inverse d to the power k p. So given that A to the power k is identity, so if we multiply P and P inverse from both sides, we will get D to the power k, which is diagonal entries are lambda 1 to the power k, lambda 2 to the power k, and lambda n to the power k, where each lambda 1, lambda 2, lambda n are the eigenvalues. So it equals to an identity matrix. Identity matrix is also a diagonal, it is also a diagonal matrix where all diagonal entries are 1. So lambda I to the power k is 1 for all I 1 less than I less than n, where since A is an real symmetric matrix, so all eigenvalues are real. I will prove later. It is given in question. All eigenvalues of A is real. It is easy part to prove. So all eigenvalues are real. So all lambda i's are real, and lambda I to the power k is 1. So only possible case is lambda I is 1 if or minus 1, and I am taking my 1 or minus 1 with if we take k is even, and only possible case is 1 if k is odd. So k may be even or odd, something like that. So whatever even odd, so lambda I square will be 1 for all I 1 less than I less than n. So lambda I square is 1 for all I. So if we take A square, that is P inverse D square P, and if we take D square, we will get identity, since P inverse lambda 1 square, lambda 2 square, and lambda n square P. which is identity matrix. So P inverse identity P will get P inverse into P will get identity. So A square is identity. So option 2 is true. What is option 3 is given? If a to the power k is 0 for some integer k. So if a to the power k is 0 for some k, so A is nilpotent matrix. We know that nilpotent matrix except A is 0 is non-diagonalizable. So only possible case where A is diagonalizable as well as A is nilpotent is A is zero matrix. Since A is a n cross n real symmetric matrix, so A must be diagonalizable, and by given condition A is nilpotent, so only possible case A is zero matrix. So if A is 0, so A square must be 0. So option 3 is true, and option 4 is easy to prove. All eigenvalues of A are real. It is an easy. So if we take since it is real symmetric matrix, so we have AV equal to lambda V. So if we take conjugate transpose, so we get A theta V theta lambda bar V theta, but A theta equal to its conjugate transpose. I am taking both sides. So since given that A is an real symmetric matrix, so there is no need to take conjugate. So whatever conjugate we have, so A transpose conjugate will be A transpose. So we have V theta A transpose lambda bar V theta. So since given that A is a real symmetric matrix, so A transpose must be A. So V theta will be A lambda bar V theta. So V theta, if we apply V on both sides, we will get AV equal to lambda V. So V theta lambda V will be lambda bar V theta V. So we will get lambda minus lambda bar V theta V will be 0. And since A is a real symmetric matrix, A is a real symmetric, and by definition of eigenvector, V must be non-zero. So V conjugate into V, it is non-zero, and whatever possible non-zero vector, whatever possible case we have, is lambda must be equal lambda bar. So this implies lambda is real. So option 4 is true. So all options are correct. This is an easy question, whatever. Thank you for watching. If you guys like my solution, please don't forget to hit like and subscribe button, and I need your support. Thank you guys. This is my new YouTube channel. Thank you guys.